This is the third and final part of our review of integration techniques. If you missed part 1 or part 2, I'll put the links in the description. In this video, each problem can be solved using two different methods, two different strategies. This will give us the opportunity to compare. For number 16, let us first solve this problem by applying U substitution. We will let the denominator equal U, so U equals cosine x. In that case, U prime is negative sine x. Making the substitution, we get the integral of sine x over U. Instead of dx, we write du over U prime, which is negative sine x. But then we notice that we have sine x in the numerator and sine x in the denominator. The extra negative sign that we see will be put out in the front of the integral. So now I have the integral of 1 over u du. But this is a memorized rule. We know that the integral of 1 over u du is the natural log of the absolute value of u plus c. Don't forget the negative out in the front. So I have negative natural log absolute value of u plus c. And of course, u is actually cosine x. So here is the final answer. Now let's do the same problem again, but this time using a memorized rule. We know that sine over cosine is tangent, so this is really the integral of tangent x dx. And here is the memorized rule that we learned for the integral of tangent x. Notice this is the exact same thing we got by the other strategy. All right, let's attack number 17, part A, applying U substitution. We will let U equal the whole denominator, 1 plus cosine x. That means that U prime will equal negative sine x. Let's see what happens when we do the substitution. We will have the integral of sine x over u. Instead of dx, we will write du over u prime, which is negative sine x. This is looking very familiar. We notice that we have a sine x in the numerator and the denominator, so they cancel each other out. The remaining negative sign will end up out in front of the integral like so, and then we will have the integral of 1 over u du. However, this is a memorized rule. We know that the integral of 1 over u du is the natural log of the absolute value of u plus c. And we do have this negative sign in front. Meanwhile, u is 1 plus cosine. So that means this is the final answer. Let's integrate the same problem again, but this time we'll do it by multiplying the top and bottom by the conjugate of the denominator. So it looks like this, but you can recognize this as the difference of two squares. So when we multiply these together, the denominator should become a squared minus b squared. So the denominator should be 1 minus cosine squared. In the numerator, I just have this sine x. Should I distribute this? I'm going to leave it for now. So I have sine x times 1 minus cosine x dx. However, this is part of an identity that we learned. It really comes from the Pythagorean identity that went like this. Sine squared x plus cosine squared x is equal to 1. So if I were to subtract cosine from both sides, I would see that sine squared x is equal to 1 minus cosine squared x. So this is the identity that we're going to use right now to make a little substitution. Instead of 1 minus cosine squared, let's put in sine squared. Next, the sine x that's right here will cancel out one of the sine x's from the denominator. So that's going to leave us with 1 minus cosine x over sine x dx. Now we would use the a plus b over c rule, which tells us that we can rewrite this as a over c plus b over c. So that gives us this so far. Of course, 1 over sine is cosecant, and cosine over sine is cotangent. Of course, we have rules memorized for the integral of each of the 6 trig functions, including cosecant. So we know that the integral of cosecant is going to be the natural log of the absolute value, well, negative natural log absolute value of cosecant plus cotangent. So cosecant plus cotangent. So that's the yellow part. And here's the memorized rule for the integral of cotangent x dx. Natural log absolute value of sine x plus c. So I'm just going to stick that right here. So we're going to have the natural log of the absolute value of sine x plus c. So this is the final answer. Now, if you're thinking, wait a minute, that does not look like what we got by the first strategy. It doesn't look the same, but there is a property of logarithms, and I'm not going to go through this entire thing, but I will say that there is a property of logarithms that we can use to simplify expressions that look like this. First of all, let's take the negative sign outside of parentheses. Let's factor that out. So this would be the same as negative natural log a plus natural log b. So here comes the property of logarithms. We know that the natural log of a plus the natural log of b can be written as a single natural log of a times b. If we apply this property to what you see here, then we get this. Rewriting in terms of sine and cosine, we now have this. Imagine on the next step that we take the sine x on the right and we do the distributive property. You can probably see that the sine in the first term will cancel out and we'll be left with a 1. The sine in the second term will cancel out and we will be left with cosine. So this is another form of the solution. And if you compare this form to what we got by the first strategy, you see they are the same. For number 18, part A, we want to transform this integral to make it look exactly like this trig rule that we're about to use. One way to do that is to factor out a constant. If you look at the rule, you see that we just have x squared. There's no number in front of it. So that 9 has to go according to this strategy. Let's start by taking the 9 outside of some parentheses like this. Okay, I keep wanting to say we're factoring out a GCF, but really there was no actual common factor. We're forcing this to factor out. So if we do that, then inside the parentheses, we will have to have 1 over 9. When you factor something out, you are dividing by that number. So I will have 1 divided by 9. And of course, if you divide 9x squared by 9, that just leaves the x squared. So we are getting closer to the rule. We wanted to have just minus x squared, and we do. But we don't need to have anything else under the radical. We just want a squared minus x squared. So this 9 needs to get on out But that's fine. We can go ahead and take the square root of 9, and that's 3, and we can bring that out. So there you go. We took the square root of 9, and that became a 3 outside of the radical. Now that we have the 3 sitting out front, we can easily see that actually we can take this all the way to the front of the radical. So let's actually erase this 3 and put it in the front as a 1/3. So this is actually now a perfect match for the rule. We just need to understand what the a value is. Remember that the a value will always be the square root of this constant. So that's going to be 1/3. All right, that's the square root of 1/9. So that is the a value. Which trig function rule are we actually going to use right now? Well, here are the 3 rules that you need to memorize. Hopefully you have already memorized. It's not going to be arctangent because we do have the square root. So it's going to be one of these two. Clearly it's going to be arcsine because there's nothing out in front of the radical. I mean, there's no variable out in front of the radical, and we have the constant minus the variable. So arcsine it is. Please notice that the arcsin rule does not have a u over a or a 1/a in the front. All right, it's the only one that doesn't. So we just immediately begin to write arcsin. We did not do u substitution, so I'm just going to do x over a. But okay, wait a minute. So if I do x over a, and a is 1/3, I'm not going to leave it like that. You know that when you divide by a fraction, you multiply by the reciprocal. So dividing by 1/3 is the same thing as multiplying by 3. So I'm hoping you can see that this will immediately become 3x. All right, there is no absolute value in this formula. That would be arcsecant, so don't forget that. And we will have the plus c on the end. Of course, we do have this 1/3 that is in the front that we pulled outside of the integral, and that is still there. So that is how you can integrate by pulling out a constant multiple. So what other strategy are we going to do now? We're going to solve the same problem, this time using U substitution. I would start with a small rewrite of the original problem because we want u squared. So we need something squared. We will have to introduce parentheses into the problem. So I have the square root of 1 minus, and I'm going to put parentheses. So I need something squared. But in order to have the equivalent expression of 9x squared, I would need a 3x inside the parentheses. If I turned around and I squared the 3 and I squared the x, I would get 9x squared. So these are the same. Now I can do the u substitution of which I spoke. The u is the thing that is being squared. So I know that u will be 3x. That means that u prime will equal 3. Substituting u for 3x gives us this. Instead of writing dx, we will write du over u prime, which is 3. But actually, we can take this 3 in the denominator and write it out front as a 1/3. So we get 1/3 times the integral of 1 over the square root of 1 minus u squared du. This integral is a perfect match for the rule, so we can go ahead and use this rule to integrate. Again, the rule begins with arcsine. There is no 1 over a or anything in the front. So it's just going to be arcsine u over a. I think I will go ahead and do the substitution now. We know that u is 3x, so it's going to be 3x over a. I should have mentioned this from the start, but in this case, a is going to equal 1. because the a value is the square root of this constant. So for this strategy, a will be 1. So u over a will just be 3x over 1, or simply 3x. And constant of integration, of course. Don't forget the 1/3 that we have in front of the integral. So we will bring that down. And that's it. That's how you would integrate using U substitution immediately. Compare this answer with what we got by the other strategy, and you can see that they are exactly the same.